Good morning, Jean-François from Chrysalide Engineering. There is a difference between Arduino and the classic IDE. That is, in the Arduino we used to program with the wire language. We're going to see what's the main difference between a simple language such as the wire language used by Arduino and the mainstream engineering IDEs. What the IDE can provide in addition with simple Arduino program language and IDE, but also what are the benefits of this. I'm Jean-François from Chrysalide Engineering. We design boards and we provide services. If you want to know more about our products, there is a website where some of these are available. We have on this window the STM32 Cube IDE, the Arduino IDE, and Moonriver Studio. These are the main frameworks provided by the manufacturers. We have here the Arduino IDE, Moonriver Studio, and STM32. We have also MCU Expresso, which is used with the NXP range of microcontroller and product. The same with Texas Instruments, and the same with Microchip, for example. Atmel Studio. So the Arduino IDE, in comparison with the others, is very simple. You don't have a lot of options. You also are limited in what you can do. But it is very portable, and all we have to do is usually include LCD, wire for I2C libraries, serial communication library, and we have a function called loop. Inside this loop function comes the main program, but we don't have access to some of the underlying hardware, say for example the interrupt, although we can program them with the Arduino IDE. Some are prefixed. For example, the timer can be used for the millis function. It can be programmed in a particular way, and the clocks can also be programmed in a particular way. So we are using the IDE with some of its limitations. That is, the processor, the library were implemented on a particular configuration, and we might lose a little bit of performance for some code we want to do. We can be limited by the implementations used in the underlying library, like the serial library, like the digital write library is also going through indirections. That is, we don't just write the pin low or high. This actually goes into a lookup table to see what is the pin for this particular microcontroller. And this uses a little bit of memory into the microcontroller, and also for every read-write operation it goes through additional code. It goes through an indirection inside of the microcontroller to map the pin we want to the controller physical pin. That's the vast variety of boards that the IDE supports, but there is a lack of performance inside of this, the way the I/O are handled. So the difference with the classic IDE, first of all, it's very difficult to understand in the first place if we are not familiar with it, because there is a location file that is what is the location we want to write in memory, in flash, what address, in RAM, what address. We have different boot mode. We can boot from flash, boot from RAM. Some configurations can be used straight away, but usually we can also tweak, and we have a lot of flexibility even in the way the chip will be programmed and will boot. And the boot itself can be simple or use multiple steps. Can have a bootloader, and can run code from RAM if we don't want to flash the program stand in RAM. We see we also need a couple libraries, peripheral libraries. There is a startup procedure, startup file. Say this one, for example, is an assembly file actually. We have the addresses of the interrupt request handlers, a little bit of manufacturer specific code for startup, but this doesn't need to be changed. But the main program is now our main.c and the main function, of course. After boot, the microcontroller will end up in this main function. The same happens with all the other microcontrollers typically. Program in C. That is for Arduino IDE. There will be a main function calling the loop. It's just that we don't have access to the main function, it's hidden behind. In Arduino we can use C and C++. Other IDEs usually provide mostly C, and we can also use C++. But there is often an impact in the footprint or for lower-end microcontrollers. So it is not that easy to use C++ typically for small embedded microcontrollers. The default is usually C. But all the advantages are, for example, we have a release and a debug build. We can build for debug and connect our probe and connect a probe to the microcontroller and see the registers. We can put hold points and run the microcontrollers, which will stop at this particular hold points. And say we just want to open and blink an LED. There we use the delay, digital write low, digital write high, and we set up the pin as an output with a pin mode output. When we are using the classic IDE, we see the behavior is slightly different. There we have to use the C, and that's why it's also much more powerful, because we have now to create a structure that is the GPIO struct accept the pin, the mode, the push-pull mode, and the speed, for example, or the alternative modes can be programmed also. So we can use the full scope of the microcontroller, and microcontrollers can be quite complex with multiplexed pins, and with this we already see what is the main difference. Now we have to use a struct and properly fill in the struct with the pin number, the proper mode, if it will be an interrupt, rising edge, or if we want to pull up, and we have to call the function GPIO init with this struct properly filled in. So we have all of this just to set up our pin to a particular mode we want. And this can be automated, it can be abstracted away if we want to program facilities. When we are using this IDE and we see the powerful capability of the microcontroller, we can tune the rising edge of the output, for example. We can have a fast input-output, or we can slow them down if we have some issues with the electronic hardware, or if our program is too sensitive to electromagnetic pollutions. And now we see that with the Arduino IDE, how are we going to make this, to use the microcontroller with its own capabilities like this. And we see that at this point everything has been abstracted away. We cannot really go into this particular configuration then unless we do the same kind of work, that is read and understand the manual, the hardware manual, and start to handle the registers of the microcontroller. Mostly the Arduino IDE, of course, works with Atmel microcontrollers. Nowadays it also works with some of the STM and ARM and RISC-V microcontrollers, for example, but in this case it will usually be limited, and therefore it's a good starting point. But then if we need to get into this kind of IDE and this kind of complexities, there is a step, a learning curve that is not easy to grasp. And the structure is like this. We have the main.c. Usually we build using a template, the program, with our microcontroller, and sometimes like this particular CH processor. It comes out to be quick, efficient, because we have everything set up for us and we can flash directly with this button. So the default is working almost out of the box, and we see that they are using nested vector interrupt priority configuration. That is, interrupt can be nested with priorities, so that a particular interrupt can be interrupted by other ones according to some priority level. Then we need to update the system clock configuration, that is, the controller will boot with a default clock, for example an 8 meg RC internal clock, and then it will switch over to something else, say for example the external crystal, that is an 8 meg accurate crystal oscillator, and a PLL, and so it will boost up to 48 MHz. At this point, inside of this we have the register setup. We see already what needs to be done. We have indirection with the configuration registers, and we are setting up the hardware to use an internal oscillator, an external oscillator, a PLL, whatever needs to be programmed through the configuration headers. Typically we have used, say for example on this header, we will define if we want to use an internal oscillator, that is an RC oscillator at 8 meg calibrated. We can use the PLL. The 24 meg is the same with a PLL to boost the speed, or PLL configuration with 20 meg or 48 meg output, and the same with an external crystal. So at this point, for example, we are using the crystal, and the oscillator will start up if we actually watch with a scope until we call the system core clock update function. The oscillator will actually not be working. It will be in standby on this particular microcontroller. At this point it will start, and the clock will switch over to this much faster and much more accurate clock. And then we can also have a backup clock, so that if the crystal ever fails, the chips can return to the internal RC oscillator. We need to initialize the serial output. Printf is used to output informations through the serial pins. Then we need to set up the internal clock. It is called systic. And this is an interruption which can be used to provide a timer for all our program. In this program we also init the GPIO and the timers, and then we have our main program. And we compare this with a simple setup in mode digital write, serial begin, interrupt setup. Thanks for your interest on this channel. We are not going to get into the core details of the complex IDE right now. If you want to follow this channel or are interested in our products, you can see the links under this video. And these programs and the samples are also available on GitHub. Thanks, and keep in touch.